Hello. In this video, we will talk about dimensional analysis. None of fluid flow related problems can be solved numerically or analytically. It's often necessary to resort to experimental methods. And since experimental works can be expensive and time-consuming, it helps to keep the required number of experiments to a minimum. This can be accomplished by a technique called dimensional analysis, which is based on the notion of dimensional homogeneity. Let's take one physical problem as the example. If we want to determine the force on a propeller, and through experiences, we know that it's influenced by the following physical properties, such as the diameter of the propeller, the forward velocity of the propeller, the density of the fluid, the revolutions per second, or how fast the propeller is rotating, and the fluid viscosity. We would like to know how these independent variables affect the dependent variable, which is the force. So we can use experimental run to determine their relationships. Here we have 1 dependent variables and 5 independent variables. Let's say the number of levels to be tested for each parameter is 5, which means for the diameter we have 5 different settings. Okay, D1, D2, D3 up to D5, and this is, let's say this is the smaller, okay, the smallest setting of diameter, and this is largest. Okay, so D1 to D5 is from smallest diameter up to the largest diameter. We did the same for all the other parameters, such like the revolutions per minute, okay, the N here, which also have 1, 2, 3, 4, 5, and 5 different forward velocity settings, and 5 different density, and 5 different viscosity. So what is the number of tests to be performed for this setting? Well, you can make a table to help you keep track. For example, when you test how the different diameter affects the force, okay, of course you need to keep the other parameter constant when you test D1 up to D5 and how the force is being affected. And then you have to upgrade these settings. Okay, the first round you perform at U1, rho 1, M1, mu1. So the second round you have to perform with U2. Okay, while the rest is remain the same, and then you upgrade rho 2, N2, mu2, and so on, until you have upgraded from U1 up to U5 and rho 1 to rho 5 and N5 1 to M5, mu1 to mu5. Okay, so how many number of experiments you need to perform actually? Well, there is an equation for this. Says the number of independent variables is 5. Okay, we have here density, diameter 1, the velocity, density of the fluids, the revolutions per minute, and up to the density. So 5 independent parameters. And the number of levels, like I said just now, is 5, okay, for each of these independent parameters. So the number of runs, okay, the number of runs for the experiment is equals to the number of level to the power of the number of independent parameters. So in this case we have 5 levels, and the independent parameters is also 5. So 5, 5. Okay. So what's the answer? You will have 3,125 experiments to be performed. Now let's say if you handle these problems by the use of dimensional analysis, then you can reduce the number of parameters involved in this problem. Okay, we know that the number of pi groups to be obtained in a dimensional analysis problem is the number of parameters minus the number of dimensions involved. Now, how many number of parameters in this problem? 1, 2, 3, 4, 5, 6. So you have 6 parameters. And the number of dimension is for each of these, okay, for each of these dependent and independent parameters, we know that the dimensions involved would be the mass, length, and time. Okay, only these 3. So we have number of dimensions equals to 3. So this is 6 minus 3. We have 3 pi groups. Okay, so the number of independent parameters in this case would be 2. Okay, which is pi 1. Okay, we have 3 pi groups, so pi 1 is the dependent pi's, and then as a function of pi 2 and pi 3. So number of independent parameters in this case 1, 2. Now the number of level to be tested, let's say we maintain the same level, so which is 5. So how many number of runs to be performed in the experimental work? In this case, it would be the number of level to the power of number of independent parameter, which is 2. Okay, so this is 25, right? 25 experiments. So let's say if you can run 25 experiments in a day, so one day you can complete all the experimental works if you apply dimensional analysis. And if you didn't, which means you are working on the physical variables, okay, physical parameters, then you need to run 3,000 over experiments, and that would require about 6 months. Okay, given that one day you can run 25 experiments, so you need 6 months. So you can see how much reductions in terms of time as well as the cost that will involve. So what do we obtain when we perform dimensional analysis? Well, the result of dimensional analysis is if given a physical problems here, okay, which involve the force being influenced by diameter, revolution per minute, the forward velocity, density of the fluid, and viscosity of the fluid. Through dimensional analysis, you will obtain a relationship, okay, you're going to obtain 3 pi groups. Okay, 3 pi groups. This is one pi group, the second pi group. Okay, another pi group will be this, the force coefficient. Okay, which if I write it down like this, it would be rho u squared d squared. Okay, that is pi 1. Okay, and this is pi 2, and this is pi 3. So we reduce the number of parameters involved by grouping the physical parameters into non-dimensional parameter, or we call it pi group. So for this particular problem, we have only 3 pi groups and we need only 25 experimental runs. So we will obtain this functional relationship. Okay, how to relate the physical parameters in terms of non-physical parameters. And of course, this is the end of the dimensional analysis. From here onwards, we will need to run the experimental works, okay, do the experiment to investigate how pi 1 is influenced by pi 2 and influenced by pi 3. Okay, sometimes you get a linear relation or nonlinear relations. You can use curve fittings to find the functions, okay, for those nonlinear relations. And for linear, of course, you know the equation, right? So that is the overall picture of dimensional analysis. It helps you obtain the pi groups or non-dimensional parameters for a given problem, and thus reducing the number of experimental runs required to investigate the relationship between force and the other parameters for a given problem. In dimensional analysis problem, of course, you need to deal with dimensions and their units. So the dimensions involved would be mass. Okay, these are the fundamental dimensions: mass, length, time, temperature, electric current. And of course, for fluid mechanics problem, we normally involve mass, length, and time, or in symbol MLT. The SI unit for these 3 dimensions is kilogram, meter, and second. So often people confuse symbol with unit. Okay, kilogram, meter, and second are their units, and dimension is in terms of mass, length, and time. Dimensional analysis is based on dimensional homogeneity. Okay, the concept of this, meaning that any equation describing a physical situation will only be true if both sides have the same dimensions. For example, on the left-hand side, okay, if you have 1 meter plus 3 kilogram equals to 4 days, we know that meter and kilogram are different dimensions, right? And days on the right hand side of this equation is on another dimensions, which is on days, okay, which is time, in terms of time. So the left hand side and right hand side of the equation, the dimension does not match, right? So this equation is invalid. And the next equation here, meter, And on the right hand side, you have also meter, right? Which is in terms of dimensions. The left hand side terms are all in terms of length, and the right hand side is also in terms of length. And therefore, mathematically, there's a chance that this equation is true, okay? But of course, how you calculate it, there's a different story. So whether the dimensions, whether an equation is valid or not valid, you can simply check their dimensions, okay, on the left hand side and on the right hand side of the equation. In other words, the dimensions must be consistent. The property of dimensional homogeneity can be useful for checking units of equation. Okay? For example, if you have equation like this, like the second one, of course, we can only check for the equation that is valid, right? So what would be the unit of this equation? Of course, it's going to be in meter, because the length would be the dimensions of these equations. Okay, you can also convert between two sets of units and defining dimensionless relationships. The methods involved in performing dimensional analysis, there are several, such as by inspection, just checking the dimensions of the equations, by ray length method. The most popular one is called the method of repeating variables, or we call it Buckham's pi theorem. In this method, there are 6 steps. This method is popular because it can systematically lay out the steps involved. The first step would be to list the parameters in the problem and count the total number of parameters, which is n. Then list the primary dimension of each parameter and count the total number of dimensions involved, which is m. And normally, for fluid mechanics problems, the number of dimensions involved would be 3 for mass, length, and the last one, time. Okay, 3 dimensions. So the number of pi groups, or the non-dimensional group that you will obtain, okay, k is equals to n minus, okay, the n minus in this m, which is normally 3. And then you choose the number of repeating parameters, okay, which is 3 repeating parameters, because m normally is 3. Construct the pi groups and manipulate as necessary. Write the final functional relationship and check your algebra. So those are the steps involved. And the result of dimensional analysis is by groups, right? Which is non-dimensional group. Some non-dimensional group often appear. Okay, you often find your pi group containing this. The first one is Reynolds number. Okay, something wrong with the equations here. Reynolds number is rho ud per mu. Euler number, okay, and so on. Okay, so some of these terms are left out, just like the Reynolds number. You can easily find them, okay, in the textbooks or from the internet. All right, that's the end of this first part of the video. Thank you very much.